Morning, my dear students. Let us start the class. Yeah, so in the last class, I was just discussing regarding the Lagrange multiplier and Lagrange multiplier theorems. So basically, that Lagrange multiplier theorem is condition theorem which is used for obtaining the necessary conditions for the equality constraint optimization problem. Okay. So in today's class, let us just proceed with unconstrained problems only. So here, so we check a necessary condition for a general constraint problem. So here what's happening, the last class when we discussed, we considered only equality constraint problem. So here we will going to take the inequality constraints also here, and we will going to obtain the necessary condition for the general constraint problem. So therefore, see what we're going to start here. It is important to understand the role of inequalities in the necessary conditions and the solution process, because most of the engineering problems, they will go to get it as an constraint problems only. So where you will going to get a constraints in the form of equality and equal and as well as the inequality. So therefore, it is very important for us to understand what is the role of inequalities in the necessary conditions and also the solution process. Because these inequality constraints, either it might be an active or inactive at the minimum point. So what we supposed to do here is, how do we determine the status of inequality at the minimum point? Is the one biggest question for us. And the answer for that question is, the determination of the status of an inequality is a part of the necessary condition for the problem. In the sense, what I need to say here is, the necessary conditions needs to be determined for a general constraint problem. The general constraint problem in the sense, so which consists of both equality constraint as well as inequality constraint. Okay. And here the question is, how do we determine the status of an inequality at the minimum point? So what actually the minimum point is and how we can determine the status of this inequality at that minimum point. So the major, the answer for this question is, the determination of the status of the inequality is the part of the necessary condition for the problem. In the sense, if you obtain a necessary condition for the particular problem, so that itself is the determination of the status of the inequality. So therefore, so in the further discussion, so we will going to have a necessary condition for a generalized constraint problem. We will going to discuss. Okay. So the generalized constraint problems, the necessary conditions, we generally call it as Kuhn conditions. We call it as, in short, we call it as KKT. KKT, Kuhn necessary conditions. So in this, we are going to discuss what is this condition and what are the most important points that needs to be considered while you are using the KKT conditions. Okay, and also we need to discuss this KKT theorem also. One theorem we will go to discuss. This KKT necessary condition is applicable for generalized constraint problem. Generalized constraint problem. Please remember this. Okay. So what we do here is, I think in the last class when we were discussing the Lagrange multipliers, so we have discussed one standard optimization model, a design generalized optimization model. Okay, so where we have considered the design variables, the optimization function, and the third important thing what we've taken, it is an equality constraint. It is in the form of hi of x. So now we will going to add another one constraint, which is consisting of an inequality constraint. So if you want, we can go back to that statement what we have discussed in the previous class. Yeah, this is the one I am talking here. So this is what we call it as a generalized optimization model. Okay. So here we have a design variable vector x, which varies from x1 to xn, and we have a cost function f of x, which is a function of x1 to xn, and we have considered equality constraint hi of x is equal to 0, where I is equal to 1 to t. So only these three equations we have considered for discussing the Lagrange multiplier or Lagrange multiplier theorem, because that is applicable only for equality constrained problems. Okay. So now for this generalized optimization model, we will going to add the another one equation, what we call it as inequality constraint. The fourth one, what I am showing here, inequality constraint. Gi of x is should be less than or equal to 0, where I is equal to 1 to m. So this is the one I am going to add it into this generalized optimization design model. Okay. So now we will going to discuss the necessary condition, what we generally call it as the KKT conditions. Okay. So this is what I wanted to discuss at the beginning of this. This is Kuhn Tucker conditions. So this is why now we include the inequality constant Gi of x less than or equal to 0 and consider the general design optimization as defined above. Okay. We can transform an inequality constraint into equality constraint by adding a new variable to it, which is called as a slack variable. See, this is what we are going to discuss the necessary, that is Kuhn-Tucker condition or KKT condition, what we call it as. So here, what it says here is when we consider an inequality constraint in the generalized design optimization model. So we have a possibility to convert or to transform an inequality constraint into equality constraint. And this is possible by adding a new variable to it. And that new variable, we call it as a slack variable. Okay? I think you might have heard this word slack variable when you are discussed in your operations research. Maybe when you are using the simplex method or the real simplex method or linear programming problems, there you might have used the term called slack variable. Since the constraint is of the form less than or equal to, its value is either negative or 0 at the feasible point. In the sense, so the constraint, what we have got here is Gi of x. So we have taken that as less than or equal to 0. Means the value of g should be always either it should be a negative or it should be a 0 within the at the feasible point. Okay. Thus, the slack variable must be always non-negative, that is positive or 0, to make the inequality an equality. In the sense, the slack variables is what you are adding to transform an inequality into an equality constraint. The slack variables must be a non-negative number, okay, to make the inequality an equality. This is what one thing you should remember. Yeah. So here, an inequality constraint Gi of x, which is less than or equal to 0, is equivalent to the equality constraint where Gi of x plus Si is equal to 0. Where Si is equal to 0 is a slack variable. Is a slack variable. The variable Si are treated as unknowns of the design problem along with the original variables. So please remember these things. So when you are answering to the question for KKT conditions, if the question will be in the form of discuss the KKT conditions or explain the KKT conditions. Okay, so you have to start with these things by just understanding, by just considering the inequality constraint into a design optimization problem model, and then taking the slack variable, and then you are writing the expression how we can add Gi of x, means how we can add the slack variable to the inequality constraints to transform it into an equality constraint. Okay, this is how we will go into proceed. Okay, their values are determined as a part of the solution. When the variable Si has a 0 value, the corresponding inequality constraint is satisfied at the equality. In the sense, when you substitute Si is equal to 0 in that equation Gi of x plus Si is equal to 0, so you are satisfying the equality constraint because the inequality is less than or equal to 0, out of which 1 will be the equality. So therefore, when you add a slack variable Si and if the value of slack variable Si is equal to 0, then you are satisfying the equality constraint for the inequality Gi of x. Such inequality is called an active constraint. So this is what we were discussing in the previous classes. Why, when the constraints will become active, when it is inactive, and when it is violated. Okay. So when inequality constraint satisfies at the equality, then we will say the constraint is active. Okay. This is what's happening here. When the value of the slack variable is equal to 0, then you are satisfying the equality constraint, and hence the inequality is called an active or a tight constraint. That is, there is no slack in the constraint. This is very important. Okay. For any Si greater than 0, for any slack value, if the slack variable value is greater than 0, the corresponding constraint is a strict inequality. It is called strict inequality. It is called an inactive constraint and has a slack given by Si. So when the value of Si is greater than 0, when the value of Si is greater than 0, the corresponding constraint will become a strict inequality, and hence the constraint is said to be an inactive constraint and has a slack given by Si. Thus, the status of the inequality constraint is determined as a part of the solution to the problem. In the sense, whether the inequality constraint is active or whether it is an inactive. That is the status what we generally call it as. So that status of the inequality constraint can be determined as a part of the solution to this problem. Please remember all these steps what we are discussing now. And note that with the preceding procedure, we must introduce one additional variable Si and an additional constraint Si greater than or equal to 0 to treat each inequality constraint. So what we do now, what we will go to discuss it now, we will introduce another one additional variable and additional constraint. Si is greater than or equal to 0 to treat each inequality constraint. To treat each inequality constraint in the sense, one is equality, another one is a less than, that is non-negative, negative number and 0. Both we call it as an inequality. This increases the dimension of the design problem. The constraint Si greater than or equal to 0 can be avoided if we use Si square as a slack variable instead of just Si. Therefore, the inequality Gi of x less than or equal to 0 is converted into an equality as Gi of x plus Si square is equal to 0. What we are doing here is, so to treat each inequality constraint, we need to add one additional variable and one additional constraint. But when you add additional constraint, so the dimension of the design problem will go to change. Okay, so therefore, when you want to avoid adding a constraint, an additional constraint, so what we do here is we are going to change the slack variable, which is in the first order Si. We make it as a second order Si square. So in such case, the inequality is convert Gi of x less than or equal to 0 is transformed, or it is been converted into Gi of x plus Si square is equal to 0. So please take this as equation number 6, where Si can have any real value. Okay, Si can have any real value. This is the one important procedure. This form can be used in the Lagrange multiplier theorem to treat inequality constraint and to derive the corresponding necessary condition. In the sense, in the last class, we discussed the Lagrange multiplier, and we can treat this form of the what we call it as the inequality constraint, and we will treat the inequality constraint and derive the corresponding necessary condition. The m new questions needed for determining the slack variables are obtained by requiring the Lagrange L to the stationary with respect to the slack variables as well. So m new equations. We need m new equations for determining the slack variables are obtained by requiring the Lagrangian L to be stationary with respect to the slack variables as well. That is, partial derivative of Lagrange L with respect to the slack variable S is equal to 0. In the sense, what this statement is saying is, we need an m number of equations for determining the slack variables. Okay, so this can be obtained. So how we can obtain the m number of equations is by just making the Lagrangian L is stationary with respect to the slack variables, as well as partial derivative double of double s is equal to 0. Note that once a design point is specified in equation 6 can be used to calculate the slack variable si square. If the constraint is satisfied at the point, if the constraint is satisfied at the point gi of x less than or equal to 0, then si square should be greater than or equal to 0. What it says here is, so in equation 6, if you specify a design point once, if you specify a design point, and we can use equation number 6 to calculate the slack variable si. If the constraint is satisfied at the point gi of x less than or equal to 0, then the slack variable si square should be greater than or equal to 0. If it is violated, then si square is negative, which is not acceptable. That is, the point is not a candidate minimum point. So this is a very important conclusion what we are arriving at. See, if si square is, if we satisfy, the constraint is satisfied at that point, at that particular point, means we specify one point, and we can determine the si square by using equation 6. Okay, so once you get the value of si square, and if we substitute that value, and if we say the constraint is satisfied at that point, constraint is satisfied means what? The condition gi of x should be less than or equal to 0. Okay, then the value of si square should be greater than or equal to 0. This is what this is. If the value of s square is not greater than or equal to 0, or if it is less than 0, or what we generally call it as a negative number, which is not acceptable, and hence the point is not a candidate minimum point. So you should be very careful while you are arriving the necessary condition for a generalized constraint problem. Okay. So there is an additional necessary condition for Lagrange multiplier of less than or equal type constraint given as uj star of uj star less than, greater than or equal to 0, where j is equal to 1 to n, which is equal to, taken as equation number 7, where uj star is the Lagrange multiplier for the jth inequality. Okay. So thus the Lagrange multiplier for each inequality constraint must be a non-negative. If the constraint is inactive at the minimum, it is associated Lagrange multiplier Lagrange multiplier for each inequality less than or equal constraint must be non-negative. Okay. If the constraint is inactive at the optimum, its associated Lagrange multiplier is also 0. If it is active, that is gi of s is less than or equal to 0, then the associated multiplier must be non-negative. This is a very important conclusion you have to arrive at. Okay. The necessary conditions for the equality and inequality constraint problem written in the standard optimization model can be summed up in what are commonly known as Kuhn-Tucker condition, first order necessary condition displayed in the theorem. So this is the KKT theorem. Okay. So I will just taken the photograph of this. So you can just read this, you can understand. So Kuhn-Tucker optimality condition. Okay. Let x star be the regular point of feasible set, that is local minimum for f of x, subject to equality constraint and inequality constraint. Okay, equality constraint is hi of x, whereas inequality constraint is j of x. Then there exists a Lagrange multiplier v star and u star m vector, which is called a p vector. V star is called a p vector and u star is called m vector, such that the Lagrange function is stationary with respect to xj, ui, uj and sj at the point x star. So it requires a little bit of vector calculus also. So please, if you have time, so you just go back to your mathematics and discuss with your mathematics teacher. So regarding what is p vector and what is m vector, because all these things are very much required. That's what I was talking in the beginning of the class. The vector calculus, matrix are very important for me in this optimization concept. Okay? Please discuss this and get a little bit of idea about all this. Okay? The Lagrangian function for the problem written in the standard form. So when we take two Lagrange multipliers, one is a V star, another one is a U star. Both are Lagrangian multipliers. So then we will write the problem in the standard form, Lagrangian function. We are writing the Lagrangian function for the problem in the standard form. This is the standard form of Lagrangian function. Okay. So, and then first one, then gradient function we have written. Double of dou x is equal to this is the gradient function we have written here. Okay, so if you understand us plus what we have done, the same thing over here we are taking. Double of dou v is equal to 0 xi of x, and here it is uj u. Okay, so partial derivative of Lagrangian multiplier L with respect to j is equal to 0. It implies that gi of x plus sj square is equal to 0, where j is equal to 1. This is the one what we discussed in the previous class, how we can get the gradient conditions. So in the last Lagrangian multiplier here, we have got last two equations, okay, which is in the form of a gradient condition. So this is what we are just converting. We are expressing the Lagrangian multipliers in the gradient form. Okay, our gradient conditions. So this is the gradient condition for Lagrange what we have. Okay, feasibility check for inequalities. So feasibility check, Sj square greater than or equal to 0 or equivalently Gj less than or equal to 0, where J is equal to 1 to n. This is the feasibility check conditions for the slack variable. Okay, and then switching conditions. This is not required. Non-negativity of Lagrange multiplier for inequality. This is another one important. Uj of star greater than or equal to 0, j is equal to 1 to n. And the regularity check. Gradients of the active constraints must be linearly independent. In such a case, the Lagrange multipliers for the constraints are. This is very, 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 very important for you. The Kuhn-Tucker optimality condition. So please, you should be in a position to understand the vector calculus and then we need to write how to express the Lagrangian function for the problem, the standard form. So this is the equation that is 4.46 as what I am talking here. 4.46. This is a very standard equation for us. Okay, so where we have two vectors, one is called V star, another one is a U star. One is a P vector, another one is a M vector. Okay, so now, and function is a stationary with respect to, so these points they have it. So you should know how to write this expression, okay, 4.46, and also how to express it in the gradient conditions. So these two things are very, very important. 1 and 2 are very important, and third one is also very important. We have to check it out for the feasibility condition. So please remember these things, because please practice these things. Not remembering, you need to practice it. You have to write down the number of times. So how we can write the standard Lagrangian function form, and how we can convert that into a gradient conditions. Okay, and how what should be the feasibility check for the inequalities, and how non-negativity of Lagrange multiplier for the inequalities can be data. This is very, very important. Please, you have to write and you have to practice a number of times, because Lagrange multiplier theorem and cohort conditions are the two most important questions in the examination point. Okay, they ask for minimum 6 to 8 marks for each one. Minimum 6 to 8 marks for each condition they will go to ask. You should be in a position to write their things here. Now, let us move on to the last thing in this chapter, that is in the module, important observations about KKT conditions. The following important points should be noted relative to the KKT first order necessary conditions for the problem written in the standard form. Okay. First one, the KKT conditions are not applicable at the points that are not regular. So I think I discussed what is regular point in the last class. The KKT conditions are not applicable at the points that are not regular. In those cases, their use may be yield candidate minimum points. However, the Lagrange multipliers may not be. Very important. Okay. So if the KKT conditions are not applicable at the points that are not regular, in those cases, their use, the KKT condition use may be yield a candidate minimum point. The Lagrange multipliers may not be unique, both are not unique. Any point, second one, any point that does not satisfy KKT conditions, any point that does not satisfy KKT conditions cannot be a local minimum point unless it is an irregular point. The points satisfying the conditions are called KKT points. In the sense, any point that does not satisfy KKT conditions cannot be a local minimum point. It cannot be. If it is not satisfy KKT condition, that cannot be a local minimum point unless it is an irregular point. Okay, so therefore, the point satisfying the conditions are called KKT points. Please remember all these points. Next, the points satisfying the KKT conditions can be constrained or unconstrained. They may be unconstrained when there are no inequalities and all inequalities are inactive. The points satisfying the KKT conditions can be constrained or unconstrained, whatever may be the points. They are unconstrained when there is no inequalities and all inequalities are inactive. So when do we say the constraint is unconstrained? When there is no inequalities and all inequalities are inactive. If the candidate point is unconstrained, it can be a local minimum point or maximum or inflection point depending on the form of Hessian matrix of the cost function. So if the candidate point is unconstrained, it can be either it may be a local minimum or it might be a maximum or it might be inflection point. So this either minimum, maximum, or inflection will depend upon what is the form of a Hessian matrix for the cost function. So this is the one important thing you should note it down. Okay. If there are equality constraints and no inequalities are active, then the points satisfying the KKT conditions are only stationary. If there are equality constraints and no inequalities are active, that is u is equal to 0, then the points satisfying the KKT conditions are only stationary. They can be minimum, maximum, or inflection points. So this is the point number 4. Next, point number 5. If some inequality constraints are active and their multipliers are positive. If some inequality constraints are active and their multipliers are active, then the points satisfying KKT conditions cannot be local maximum for the cost functions. They may be local maximum points if active inequalities have 0 multipliers. So this point is very important. If you have some inequality constraints which are active and also their multipliers are positive, then those points which satisfies the KKT conditions cannot be a local maximum for the cost function. This is very important. Please make a note of this. The inequality constraints which are active and are having their multipliers positive, the point which satisfies the KKT conditions cannot be a local maximum. And they may be local maximum points only when their active inequalities have 0 multipliers. If the multipliers for the active inequalities are 0, then only the points which satisfies the KKT conditions can be considered it as a local maximum. Okay. Then the 6th point is, it is important to note that value of the Lagrange multiplier for each constraint depends on the functional form of the constraint. In the sense, so when you are introducing the Lagrange multipliers, the value of that Lagrange multipliers for each constraint will depend on the functional form of the constraint. So what kind of function that the constraint is having. So based upon the constraint functional form, so you can have the value of the Lagrange multiplier for each constraint. So these are the 6 important points that needs to be noted down. Okay. So related to first order necessary condition. Okay. Then the last thing what I want to discuss in this module. So this is the last point. The summary of KKT solution of which. So let us wind up this. Note that the following points regarding the KKT first order necessary condition. The conditions can be used to check. The conditions can be used to check whether a given point is a candidate minimum. The conditions can be used to check whether a given point is a candidate minimum. The point must be feasible. The gradient of the Lagrangian with respect to the design variables must be 0, and the Lagrange multipliers for the inequality constraint must be non-negative. So please understand these points. The conditions can be used to check. The KKT first order necessary conditions can be used to check whether the given point is a candidate minimum. The point must be feasible. The gradient of the Lagrangian with respect to the design variables must be 0, and the Lagrangian multipliers for the inequality constraints must be non-negative. So these are the conditions that needs to be satisfied if we use a KKT conditions for this KKT first order necessary conditions for checking the given point is a candidate minimum. First one is point must be feasible. The gradient of the Lagrangian with respect to the design variable must be equal to 0, and the Lagrange multipliers for the inequality constraints must be non-negative. Okay. the second important point is, for a given problem, the conditions can be used to find, for a given problem, the conditions can be used to find candidate minimum point. Several cases defined by switching conditions must be considered and solved. Each case can provide multiple solutions. And the third important point is, for each solution case, remember to check all inequality constraints for feasibility. Check all inequality constraints for feasibility, whether it satisfies j of x less than or equal to 0 or si square is greater than or equal to 0. Calculate all of the Lagrange multipliers. Okay. And the last one is, ensure that the Lagrange multipliers for all the inequality constraints are non-negative. So these are the three important points. The summary, what I am doing is a summary of the KKT solution approach. Okay, students. So I think this is the end of the module 2. Okay. So we have completed the module 2. So there are plenty of mathematical expressions, mathematical equations, everything was there. Okay. So you have to practice. So 2 units we have covered here. One is optimization problem formulation, and second one is optimization concepts. Okay. So if anything clarification, you can unmute yourself and you can have an interaction with me. So you have to practice. You have to practice number of times, because plenty of mathematical equations, mathematical expressions are involved, and you have to practice quite a number of times. There's plenty of equations involved. Okay. Friends, any clarifications, any doubts, anything, you can talk to me. Feel free. Sandesh, are you there?
Yes, sir.
Okay. So this is the completion of module 2. Okay. So please practice these things, because a lot of things are being covered in this, and I will be just uploading all the PPTs in your Google Classroom. And please try to understand this, try to note down the things properly, and you have to practice. Until unless you practice, it's not possible for you to get the things. Okay, anything to ask, any clarification is required for you, because from next class onwards, I will be starting with a new module. Okay, so before that, I want to just have any clarification, any doubts with you people, whether are you following, or be able to make the things clear with you people that I wanted to know.
Sir, we can't find notes in Google Classroom.
Sorry? Hello?
We can't find notes, sir. PPT in Google Classroom.
Yeah, PPT, I'll put it in the Google Classroom. PPT is visible.
There is no note, sir.
Hello?
There is no note, sir.
Okay, I will just put all these things in the Google Classroom PPTs. You can note it down, because notes is almost same thing only. Okay, because purely it is a mathematical steps only involved. Everything I have taken it from the textbook and I put it in the slide only. Okay, so all these things slides will follow is nothing but the notes for you. No separate note can be done. So PPTs can be taken as a notes and you can start doing. And I will go to post some more problems for the assignment problems, and those you can solve and you can keep it with you. From next class onwards, I will start.
PPT is also not there.
I will put it in the Google Classroom. Today or by tomorrow, I will put it.
Okay.
Next class, I will go to start with a new module. Okay. So,